to practically where the footpad was on Apollo 11. When they landed. I mean,
Well, I got within,
oh, here.
uh,
I thought I should have one. It's
I photographed
buried
within-
somewhere down
a couple of miles of it,
Mhm.
and I could tell because of the little crater that was
Right,
there.
right, yeah.
So,
Yeah, I come in it from,
But frankly, that was not a very interesting area.
but I say, but it's what, people are always interested in that. You do photography,
I tried.
that's your manual.
Okay.
Russ, we have an astrophotographer here. And Sanford's here. Hello, Sanford.
Hello.
Oh, and I got it.
Well, it is 7, but should we allow a few more minutes, do you
Oh,
think, or
we
should
could.
go
Yeah,
ahead
let
and
people get
plunge
their
ahead?
names on the little sheet there.
Yeah.
Have you been here before?
No.
Oh,
You
welcome.
remind me of somebody who did. Well, cool. We're glad to have
Well,
you.
I donated an 8-inch Dobsonian. I think you came and picked it up.
That's entirely possible.
That was several years ago.
Mm-hmm. Was that at, by Gage?
Fleming Place.
Yes. Yeah, I remember. Uh-huh. Yeah, so, but somebody
I didn't have a
got that.
telescope for quite a while. I got
Uh-huh.
a new one, and now I'm kind of trying to get back into it.
Uh-huh. Yeah. That's cool.
What'd you get?
It's a Celestron 8 SE, the go-to mount,
Mm-hmm.
which frustrates me to no end. 'Cause It's harder to drive than the Dob.
Well, anything's harder to drive than a
Yeah.
Dob, really. But
Well, I have an old-fashioned equatorial mount on that I bought a telescope for Halley's
Come on in.
Comet, so that's how old mine is.
oh yeah.
So, yeah.
Well, hi there. We got a thing going around, but we know you.
I think so too.
Yeah, we've got to do introductions and everything today.
Okay. This is my Christmas present. I'm one of the cool kids now. I have one of these.
Oh,
I found out that I probably shouldn't use this in my classes though, because the old kind, when you let up on it, it turns it off. This one stays on.
It didn't have a different add-on where it does that.
It might actually. I don't know. I haven't really.
It was the one. It should have with one with a little curly cable.
Oh,
and
is that
one's
what that
more
thing
of
is?
a that one's more of a you hold
he's
and
also
press to keep it
one
on.
of our tech
Okay,
members.
I'll have to check into that. But this one is
Where'd
probably
Gary go?
powerful enough that if you hit somebody in the eye with it, it would.
Oh, yeah.
not be
Well,
good, so.
Yeah.
But I did use it in class the other day, and it was quite handy. So
Yeah, we know you, but where'd Gary go? Oh,
I
he
think
left his
he
drink.
left his drink. I think he
Mhm.
make a visit.
Well, when he comes back, we need to do
Yep.
introductions. Go ahead, the people.
We'll commence as soon as Gary returns.
Yes. Gary is he was a founder and he's the ultimate guru of the world when it comes to asteroids. Oh, that's something that we can tell them is about, that thing that came in about Dave and on the Tombaugh.
Yeah, I got it in the.
Good.
It's on the list of things, along
I'll
with
sign you in, Russ.
along with
I'll sign you in.
a new unit for measuring the size of asteroids.
I saw that.
Did you?
Yeah.
Did you see the article in the Atlantic?
No,
Where
it's-
they've used all kinds of different things as size
Uh-huh.
comparisons for asteroids. There's actually, I think the current edition of the Atlantic has an article about it. I've got a link in the,
Okay, yeah, good, because I remember seeing that, and then I wasn't able to sit and read it all, so.
yeah.
Of course, my computer is, I think it's possessed. I
So
kind
how
of,
do they do that? What, by the amount of light? or-
It's, no, this is more like relative size. We'll get to that.
I know.
But they've come up. They've tried to use various things over the years as size comparisons. Hello, Angel.
Hey,
And they're really starting to scrape the barrel as far as imaginative things, and there's a bit about that coming up. So.
okay. Come on, take the.
Hi, Angel.
I'll sign you in here.
Hello.
Okay, shall we go ahead and?
Yeah, as soon as certain people quit discussing
No.
toys.
Plenty of time for that later. Cool. Well, welcome everybody. We have, at least to me, several new faces. So perhaps we should have a round of introductions. My name is Doug Gooden. Who wants to?
Russell Valentine.
Lynn Kress.
Melissa Dunn Everskirt.
Brogan Eversford.
Gary Hood. Parker Lissy.
Angel Romero.
Sam Pomeranz, I'm the psychiatrist, and makes sure the group
Yes, we
stays-
need him. He's always busy with us.
He's got a big job.
We have to.
Oh, yeah,
Yeah,
yes.
he's probably the most, essential person.
And I'm Janelle Burgart. Where are you guys from?
I'm from Topeka.
Are you from Topeka? Okay.
Yeah. And we've been out to Park Point, before.
Ah.
Yeah.
That was a long time ago.
Mm-hmm.
So,
Well, it's getting to be that time of year again.
yes.
Mm-hmm.
All right, okay,
So
so.
you're here. You're local, right?
Lawrence.
Oh, that's right. He told me. See, I need medication, or I've had too much. I don't know which.
And also, so Laura says she's waiting for the connection to start.
Oh, you mean the downstairs floor?
No, the back in Manhattan, Laura, my
Oh,
wife.
that one.
She's,
Oh, gotcha. Yes.
Mm-hmm.
Thanks. I forgot a part.
okay. Russ is working on it.
Should be good now.
Okay.
Okay, should be
That was
good.
my fault.
So I think there's a couple of people that we're planning on attending remotely. So for those of you that are planning to attend remotely, if you're already on, welcome as well. Okay, so let's go ahead and proceed. Did everybody get a chance to sign in?
Mm-hmm.
Okay, good. And by the way, I'm so happy to see new faces. So
Yes.
welcome everybody. Okay, so first of all, just a few kind of announcements and club business items. These are the schedule. This is the schedule of upcoming meetings. Obviously, you know about this one because you're here. This is what's upcoming as far as dates go. Gary, have you had any more contact with Mike?
Yes, I don't know if he's gonna be, I assume he'll be ready for the February meeting.
Okay.
I don't know.
Well, I should.
He's getting over his pneumonia, if anybody does get over pneumonia, but it's taken him a long time. So,
Well, and that was
but
kinda-
he's getting better.
That was kind of the last communication I had with him, was he had pneumonia and then it thought it was over and kind of relapsed or something like that. And anyway, he had,
As common.
and Mike Ford is the director of the Banner Creek Science Center, which is in Holton. And he will be giving a talk at, we hope, a soon meeting. The other thing that I thought was kind of exciting was Murat Ratra, who's a faculty colleague at K-State in the physics department, who's a cosmologist, a theoretical cosmologist by training, has offered to give us a talk. I haven't set a time or a date with him yet. I know he can't do February, so it'll be sometime March or after, but that would be super exciting. Some of you know Murat. He did his PhD at Stanford, and his advisor was Leonard Susskind, who is a world-class eminent physicist. Actually once won a bet with Stephen Hawking about something to do with radiation. So, and then I think Murat left there and went to become a postdoctoral fellow at Princeton, and his mentor there, the guy I worked with, was Peebles, whatever his first name is, but he won the Nobel Prize 2-3 years ago. So, this guy is just absolutely brilliant, man. So I'm super excited about that. He's a super nice guy.
Yeah,
I don't know him
he's a
that
nice
well, but he's just a great guy. So
I've
anyway,
known him for a long time.
I've known him for a while, just not well.
Yeah.
But he's a University Distinguished Professor at K-State, which is the highest thing you can be. That's a rank above me, basically. So I'm super excited about that. Anyway, so this is our schedule for meetings coming up. Have we actually resolved the schedule for club nights and public nights and all that? I know
That's
there was still kind of
being
in
debated.
still kind of
We
pending.
do have all the reservations for the rest of the year for here.
Okay,
So we're set
okay.
on that one.
All right.
But
Okay, so anyway, this is what is upcoming here. Let's see, a few other announcements. I wanted to kind of give a shout out to Dave Cromer, who's not here, but I think Gary sent this around. This is, what this is, for those of you that perhaps have not been here before, is one of the major activities, observational activities of the club is NEO follow-ups, and Gary here is our kind of the director of that particular project. And well, Gary, do you want to tell them what it is that NEO follow-ups are all about?
Well, we just want to keep rocks from falling on our heads, actually. Just,
You know, some
Yeah.
days.
yeah, there are times.
There are times when you just kind of say, would you please just nail me now? But
Yes.
No, we've been doing this now for over 2 decades, so we've got a reputation of going after near-Earth objects, and generally to do follow-up observations. The trouble with finding a near-Earth object is that they can get lost really quick if you don't follow up on them and be able to determine an orbit over a longer period of time. Okay? The longer period of time gives us much better accuracy on how to predict it down the road. So that's what we've been doing, and we've been pretty good at it. We're 10th on the list here of observatories around the world doing this. So.
And what is even more amazing about this, I think, is, the Farpointing's 10th here, but if you look at who's in line ahead of us, this is a professional observatory, well-funded, I think mostly funded by the U.S. National Science Foundation. This one, I believe, is a German observatory, also federally funded, also staffed by professional astronomers. Cerro Tololo is a huge observatory in South America. I think Great Shepherd is a amateur.
That is an amateur.
And I think Mayhill also as well, perhaps?
Mayhill is, well, I'm sorry, I think it is, yeah.
But the point here is that this is, for a amateur organization staffed by volunteers and, funded on a very narrow shoestring. This is pretty remarkable, what has been accomplished
In
here.
a very murky climate.
In a very murky climate. Do we need to say anything about, I guess the Tombaugh is pretty much back in action.
It's going. We had some issues with collimation again, so we were working on that last time. We didn't get it resolved, but I think it will resolve fairly quickly. The problem is we're going to have good, decent skies in order to do the final collimation, so we haven't had those for a little bit.
But we just recently upgraded our facility, our telescope. Those of you who've been out to Farpoint may have actually seen this, but it now has, the mirror is the same size now, but it's a faster mirror, so it sees a bigger piece of the sky. And it's been accompanied by a new camera that has a much wider field of view and is more sensitive. So it's really made the NEO searching activity, or the NEO follow-up activity, much better. So anyway, so I just wanted to unfortunately Dave's not here to receive praise, but he's the one that, and Gary, I might add, has made this list numerous. I think you're on the most recent one, right?
No, I'm not on the most recent one.
Okay, I thought I saw one of them in there.
I took a break.
Okay, but anyway, he
got
has
sick.
been on this, his personal observatory. He's been on this thing more than once, I'm sure. So this is quite an accomplishment, I think. So I just wanted to kind of give a kind of a shout out to those guys. Let's see, what else? Oh yeah, this is something I think Dave sent around. I thought I'd point this out. By the way, I've been, always sort of feeling like I need to tweak what we do in these meetings a little bit, just to try to make things a little less tedious for you. And so I'm kind of cutting back a little bit on the news stuff, largely because Janelle sends out 3 or 4 of these things every day, and after a while it's like, why am I doing this? But there's a few things a couple of things I kind of wanted to point out. This is one of them. So of course there's this comet that's visible now, and it's there's today. So unfortunately we haven't had really good skies to watch this, but this is kind of where it's going to be. It's right between the bears, basically. So if you want to take a look at that, and there's some clear skies, that's where you do. It should be pretty easily visible. The last comet that came through, I think it was the Pan-STARRS or whatever, a couple years back, was a pretty good binocular object. We watched it a couple of times with binoculars. But anyway, so this is something that if if we have some clear skies, should remain visible for quite a while now.
Right now it's in the morning
Penguins.
sky. And,
Yeah.
Yeah, you'd see it in the morning. So that's one little bit of news I wanted to pass along. This is the one that has kind of attracted a lot of attention.
Yeah.
This happened today, I think.
Yeah.
In fact, there was some online places you could look at that. This is one of those near Earth asteroid or Earth crossing asteroids. This is 2023 BU, and this kind of caught my attention for a couple of reasons. You know, almost on a weekly basis now, there's a news item that says giant asteroid headed towards
Oh.
Earth, and usually it's, you know, not that close and not that big. This one is really not that big, but it's really close. This is kind of, you know, Grays. This is super close. So it was kind of noteworthy for that. It's a relatively small one. The other reason why this kind of caught my attention, though, is one of the things that has become kind of interesting to me is the things that people compare asteroids to in order to get at their size, right? And I kind of ran into this a little bit because one of the things we do on public nights is give a little spiel on, you know, asteroids and stuff out at Farpoint, and I'm always trying to think about how big these things are, and so I made a diagram of a object that would have been about the size of the one that hit Arizona and made Meteor Crater, and sitting inside a football stadium, and it's, you know, it's smaller than you might think. This one, they compared it to the size of a London bus, which is kind of marginal for what can actually make it through the atmosphere. You know, something has to be a certain size in order, composition plays a big role in that too, but for most objects, something much smaller than this, or even this size, will break up in the atmosphere, and it'll come down in a bunch of pieces instead of one big piece. But I thought that was kind of interesting, that, and just very close it is. So, you know, there's the mean distance to the moon, right? It's inside the orbit of a lot of geostationary satellites, which orbit at an altitude that is such that they stay over the same spot on Earth all the time. So a lot of like TV stations and communications satellites and stuff are that far, and this thing is much, much closer than that. So I thought that was pretty interesting. But again, I was really struck by this size comparison thing. And of course, you get the inevitable headline that this thing is
Oh,
going
yeah.
Right.
to, you know, a terrifying 3,500 kilometers from the Earth, which is pretty dang close, but it's not, this is not really all that dangerous. But you see a lot of this. I guess it's just, you know, headline clicking, really. That, but here's the thing that I wanted to kind of sort of circle back to, because this notion of what people are comparing things to has become pretty strange. So here's the most strange one of all, in my opinion. Two asteroids the size of 22 penguins.
But are we talking,
So-
you know, emperor? Oh, it says emperor.
So
Okay,
emperor
they're different.
penguins,
now.
I remember seeing them once upon a time.
They're
They're
big ones.
about a meter tall, I would say, perhaps. They're vicious little creatures. You don't want to be anywhere near them. But so
This reminds me
22.
of there was a meme one time that said Americans will use anything except the metric system.
Yeah.
Yes.
Well,
Oh, I know.
now we have penguins,
I
and
know.
I'm beginning to think everything should be measured in penguins. Now, you know, we should give
Yeah, as long
everyone's
as they
heights in
specify
penguins.
it's emperor and not, you know,
we
like
should give
rock
masses in
hoppers.
penguins. You know, everything should be referenced to penguins. But this was, I thought, just hilariously funny, and actually this kind of got picked up, and you see this up here. This is a link to an article in the current edition of the Atlantic Monthly.
What about
magazine.
the giraffes? It says asteroid penguins, giraffes.
They had everything as references in here, and they were. It was kind of a, you know, riffing on this whole notion of comparing asteroids to weird things.
Yeah.
So
Of
anyway,
course,
the
if-
penguin
when you,
one
when you
was.
watch, you know, just other science things, the two things they always like to compare things to is either Long Island or the Empire State Building.
Mhm.
I haven't seen either one of them. It doesn't mean beans to me, but 22 penguins is not a bad, you know, you got a pretty good idea what that thing is.
Yeah, yeah.
Yeah.
So, I mean, I think maybe we need to start a movement to now make the penguin the fundamental unit of all measurement. Anyway, so I thought that was funny, so I threw that one in there. Okay, so that's about it. Oh, one other thing that's not so, but I've
Yeah.
always have been a huge fan of the space program, and, you know, it was kind of one of these things as a child. I was glued to the whole thing, and so I just wanted to kind of give one final bit of news. Today is the NASA Day of Remembrance. It's the day in which all the NASA crews that were lost in the in the prosecution of space, I guess you could say, and space travel are remembered, along with the Russian cosmonauts that as well. So this is the day. And one of the things that I always was strike me about this of course was the Apollo 1 died in a fire during a training practice. They weren't even in space at the time. This was the Challenger crew that about 1986, I guess. And then this was, I can't remember what this one was, Columbia, but not so long ago. And we always see the pictures like this of these smiling, confident, brave people. Here's what happened to them, I know it's not a pleasant thing to think about, but I think it always behooves us to remember, how special they really were and brave they really were. So I like to I worked briefly at NASA once upon a time, and it was you were always aware of that. So anyway, so I thought I would just kind of pass that along as well. Okay, anybody else have anything they want to?
I have an anecdote.
Okay.
I can throw in on this. This was in '86 when the Challenger blew up. I was on my way back from Granger after buying a motor for a mount that I built for the Dobsonian to do a platform mount. And I heard it on the radio, and I was going back to work. I worked at Channel 12 in Wichita, and I had applied for Journalist in Space. And they put me on the air, and I didn't know what to say.
Yeah.
It was the most horrible day. We were all just stunned. But I said, we can't stop.
Yeah.
We have to keep going.
Yeah.
And that's the only thing I remember about the interview.
Yeah. But anyway, I just thought I'd throw that in because today is the day of remembrance.
Yep.
All right. Any others? Thanks for that.
About 16 hours ago, I turned in data on 2023 BU, which was the asteroid that was going to come so close and already came close. But that's one of the last few to turn in observations on.
Okay. Yeah. Okay. All right. So now, turning to other topics. Again, one of the things I've been trying to do over the last several months is just kind of, focus on a piece of the sky, basically. Then, typically, I try to do one that's prominent at the particular time of year. And Laura and I, my wife Laura and I, were talking about this the other day, and I asked her, what would be a good thing to do? And she suggested the Pleiades, and I never really thought about that, but then I thought, let's. So I thought we would focus a little bit on the Pleiades, which are not really a constellation, of course, they're more of an asterism or a star cluster, but and then a little bit about the constellation that they're in. And it turns out the story is really, really interesting and has gotten even more interesting recently, interestingly enough. So I thought I'd kind of spend a little bit of time talking about the Pleiades and maybe even in a broader context a little bit. So as far as where the Pleiades actually are, this didn't show up as well as I had hoped. It's kind of cut off at the top. There. So here's constellation Taurus right here. There's my way of finding it. There it is right there. My way of finding it is always to find one of two constellations that I know, one of which is always Orion, and the other one is usually Cassiopeia, and then draw lines.
Yeah.
So if you connect the dots on the belt of Orion, it points pretty much right up to the Pleiades. And then, of course, there's this other star cluster called the Hyades, which enters into the story as well. So I'm going to kind of work them into this as well. So we're talking about this piece of the sky right now. I think this, I captured this from Stellarium yesterday. So Mars is probably still pretty much there, isn't it? So if you want to see Mars now, it's in Taurus as well. Anyway, so what about the story? So again, there's the Pleiades, the star cluster right there. The Hyades is actually the eye of the bull, sometimes it's thought of. And the story that kind of connects these turns out to be interesting. So I wanted to kind of talk a little bit about that. So the Pleiades, always referred to, or very typically referred to as the Seven Sisters. There's a reason for that. It's one of the nearest open clusters to Earth. It's referred to as the Seven Sisters. I have a hard time seeing more than 6 of anything, and it turns out there's a reason for that as well, and it enters into the story a little bit later. It's a relatively young group of stars. In fact, if you look at photographs of it like this, it's always surrounded by haze, and that haze is the leftover stuff, right? It's the material that was not incorporated into the star. So it's about 75 to 125 million years ago, which is, baby stars in the broad scheme of things. There's actually about 800 stars. They're mostly these hot, young, kind of blue stars. It turns out that there's also a lot of brown dwarfs in the Pleiades. A brown dwarf is a object that's somewhere between a planet and a star. It never really got nuclear fusion, right? It wasn't dense and hot enough to actually start squeezing together hydrogen, but
Called a failed star.
a failed
lot of the
star.
time.
I
Yeah.
would prefer to think of it as a successful brown dwarf. Let's not diss the poor things, but anyway.
Brown's the color of
But they
chocolate.
kind of are actually failed stars, I guess you could say. But anyway, there's a bunch of them in the Pleiades. They're not really going to enter into our story. The other reason why it turns out the Pleiades was kind of an interesting choice is the thing I want to talk about later about distances. We're going to circle back to these because
Yeah.
turns out they're very important for one of the links in the chain of how we know how far away things are. So, Seven Sisters. The Pleiades also kind of have a little bit of a presence in other areas, not just in astronomy and in mythology and all that. This is one from Material Culture. If you've ever driven a Subaru,
Yeah.
you have a Subaru.
I got it because of this.
We had one growing up. Our family car at one point was a Subaru. And if you ever look at the Subaru logo, it's actually 6 stars, and it represents the Pleiades. And apparently, the story that I heard is that Subaru in Japanese means something like the unity of, or the addition of, or something like that. And there were these 5 automobile companies that decided to become one, and so the stars represent the original 5 and the new one, and they just decided to kind of use the Pleiades as their emblem, right? But you also notice it has only 6 members, which again, that kind of becomes a thing later on in the story. So yeah, an asterism that has a lot of kind of presence in many aspects of culture. But if we start looking at it from the kind of mythological perspective, which is kind of what I wanted to take a little time with here, it turns out there's a lot of different myths associated with it. I thought I'd start with the Greek myth, or at least lead with the Greek version, for a couple of reasons. First of all, most of the kind of Western perception of astronomical objects and constellations and all that sort of thing, we sort of derive those from Greek mythology, Greek and Roman for the most part. But they're certainly not the only ones, and there's many kind of rich cultural heritages that look at the sky in a similar way, but with different features. But as far as the Greek myth goes, the Pleiades were what were called Oreads, and an Oread was a mountain nymph, or a mountain, and I believe this is also the derivation of Mount Oread, which is, of course, in Lawrence. It's the hill that the KU campus is built on. I think that's where that kind of came from. But the Oreads were basically nature deities. The nymphs were sort of deities of nature. They represented forests and mountains and things of that nature. The Pleiades themselves were the daughters of Atlas and Pleione, which is, I believe, where the name is derived from. Pleione was an ocean deity. Atlas was a mortal, I think, but maybe one of the gods. But Atlas, of course, later became kind of sentenced by the other gods to carry the earth around, which also enters into the story. So they were the parents of the 7 sisters, the 7 Pleiades. And they were also, I believe, Atlas also had, the Greek families were kind of messed up, right? Or at least Greek mythological families. So Atlas had another family. He had 5 other daughters by a different mom, and they were the Hyades. So the Pleiades and the Hyades are half sisters, and there were 5 Hyades and 7 Pleiades. I think there was a total of about 15 kids in this whole melange. Again, one of them kind of becomes a little bit of a part of the story later on. But all of them, the Hyades and the Pleiades, they were known for a number of things, including being the teachers and handmaidens of Dionysus, which was a god of like drinking wine and things like that. One of them, maybe actually, one of the sisters, but not any of these, may have actually eventually at one point married Dionysus, which again, Greek families get to be very, very convoluted after
More
a
of
while.
a
It's
family
Greek.
web than a family tree.
Yeah, there you go.
Yeah, yeah. But anyway, so there's an artistic representation of the Pleiades. This is in the Metropolitan Museum of Art. Well, anyway, these are who the Pleiades were in the Greek version of the story. And as I said, they were half sisters of the Hyades. So if you look at where all this is, right, the Hyades and the Pleiades, they're both in the constellation Taurus. They're both kind of close to Orion here, who's going to enter into the story as well at some point. The Hyades were also nymphs, but they were a kind of a different type of nymph. They were rain nymphs, and they're often depicted as crying, fountains of water coming in. So this is I don't know who drew this, but this is a representation. There were 5 of them. They were also kind of noted for being rather melancholy, crying all the time. And the heliacal, the time of rising of the Hyades is also closely associated with the rainy season in a lot of places. And it's thought that there's some linkages to that. Like, for example, in Native North American cultures, there's an association of those things. So the Hyades are going to enter into the story of the Pleiades as well. So, how did all these sisters become stars? And it turns out there's 2 stories here, both of which I think are pretty interesting. One of them is more common than the other, at least by my quick and rather cursory reading of the mythology that's associated with all this. In one version, this is Hyas. This is one of the sons, one of the brothers of the Pleiades and the Hyades. He was noted as an archer and a hunter, and died as a result of, I believe, being either bitten by a snake or attacked by a bull. And in most cases, it's bitten by a snake. So he died, and this produced, great lamentation and sadness on the parts of all the sisters. The Hyades, who were kind of prone to sadness anyway, became distraught, and in order to kind of cheer them up, they were made stars. Zeus made them stars, and so they went into the sky as a cluster. The Pleiades were made quite sad by this because, they were half sisters, but they were sisters and close, apparently. And so they became distraught. And so Zeus put them in the sky. So they became in the similar part of the sky. That's one version of the story. It's probably as far as I can tell, the less common version. The more common version of the story involves Orion and Atlas. So this is Atlas. This is some artistic depiction of Atlas, and of course he's carrying the world. He was sentenced to do that by the other gods. I'm not exactly sure why, but this apparently made the Pleiades quite sad that their father had been sentenced to this toil of carrying the earth around, and it also meant that Atlas, who was a mighty warrior, was no longer available to protect them from Orion, who apparently was quite adamant in his pursuit of them. Was very, very diligent, and the Pleiades apparently wanted no part of this, so they appealed to Zeus. There's Orion right there, of course, the hunter. They appealed to Zeus, and Zeus came to the rescue and put them in the sky in the form of a flock of doves. So the Pleiades, actually in Greek, derives from a Greek word that means the doves, and that's the origin of the 7 Pleiades. They are to represent doves. Of course, they're still in the sky, and Orion decided that he wasn't going to give up that easily, so he went into the sky, and so now he forever chases them, right? And that's kind of the story. That's the Greek story. It turns out that this is where I thought this got really interesting. It turns out that there's way more to it than this. This was the Greek version of the mythology. But if you look at the myths associated with the Pleiades and the Seven Sisters and all of that stuff, it's really consistently found across almost all cultures, across almost all continents. There are almost no deviations from this. Here's just a very, very few examples. This is, I wrote this down so I would forget, Skanda, the Hindu god of war. And he had 7 mothers, so the 7 mothers of Skanda were considered to be the Pleiades, and Skanda himself was Orion, so a similar labeling of that particular star group. This is an artistic representation from Australia, and this represents the sisters over here. They were called the Napalgari sisters. And they were pursued by a hunter called Wardilia. This is the representation there. So this is an Australian Aboriginal, but it's almost the same story, right? We're starting to see this same story repeated over in very different cultures. This is one from the Kiowa. This is North American, Native North American. This is Kiowa. This is Devil's Tower in Wyoming. And the story on Devil's Tower was that there were 7 Indian maidens, 7 Native maidens who were trying to escape from a bear, and they were placed on top of Devil's Tower by a benevolent god in order to keep them safe. So the reason why, if you ever seen Devil's Tower, it has this big crack work on it. And
Oh, yeah.
back in my younger days, I was a rock climber, and one of the most intense and difficult climbs I ever did was Devil's Tower, because it's long and straight up, but and you climb in one of those fissures, right? But those were thought to be the claws marks of the bear trying to get to the top to these. And of course, the constellation of the bear is not too far away from all this, right? So again, there's this consilience in all of these things. This thing right here is actually a Bronze Age shield from Germany, but it has the Pleiades represented on it. This is from the Kabbalah. This was a symbol that represented the Pleiades. So throughout all of these cultural groups, this similar story has repeated, and that sort of suggests kind of a common origin. And so there's actually been some work on this. This was a paper that was published a couple years back. In a journal or in a book called The Historical and Cultural Astronomy, which I never knew even existed. But what these authors have suggested is that all of these stories originated in Africa a very long time ago. And they estimate those ages about 100,000 years. And that's not just a number they grabbed out of the ether. There's a reason for that number. But they say, and if that's the case, then this story of 7 sisters would have come out, one of the theories of human population of the globe is that humans, anatomically modern humans, evolved in Africa and then migrated out of Africa. It's called the out of Africa theory, right? And that would have happened such that this story could have been carried along. So this may be a very ancient story. Now, it's very speculative. I don't know if this is really true or not, but it's a really interesting idea. But the piece of evidence that they point to this gets back to this notion that you always hear the Pleiades in throughout all these myths and legends and various tales referred to as the 7 sisters. But if you go out and look at the Pleiades, even if you look at it through the binoculars, you count 6, all right? I always sort of wondered about that when I was a younger person. Why are these things called the 7 sisters? Because that's what I'd heard them call. Well, it turns out that there are 2 of them, Pleione and Atlas, that are really close to each other. So close that they look like one when viewed. But about 100,000 years ago, they would have been distinguishable by a person with good eyesight. So again, this is a pretty tenuous thread of evidence, to be really honest with you, but Here's a simulation of what they might have looked like. This is what they would have looked like now, essentially. This is what they would have looked like 100,000 years ago, separable, close but separable. So the speculation is that perhaps this myth has traveled along with humans, and if that's the case, it may be one of the oldest human stories. So, the Pleiades kind of started off for me as just kind of a, an interesting thing that I had seen. And it turns out it has a really pretty interesting story associated with it. I'm going to have to look up this article here when I get a little spare time for reading, because I'm really curious about it now. So anyway, that's the story of the Pleiades. As far as other things that the Pleiades are useful for, they are a very well-studied, astronomically, scientifically well-studied star group. But one of the things they were used for quite recently was to help calibrate the Kepler Space Telescope. You might know that the Kepler Space Telescope was launched to search for exoplanets, right? The way that it does that is by looking for very, very minute changes in brightness, which mean that something has passed in front. And of course, stars vary in brightness for a lot of reasons that have nothing to do with little planets passing in front of them. So in order to calibrate effectively, you have to be able to kind of compare to stars that are fairly well understood. So that was one of the reasons why they pointed this thing for quite a long time. The other thing is that these are really bright stars, and the Kepler is designed to look, the Kepler telescope was designed to look at very faint stars. And so in order to kind of establish upper limits for calibration, they used this as a calibration target. So even though it's scientifically pretty well studied thing, it still contributes to astronomical science. There's Pleione and Atlas right there, by the way. And here's another thing about it, and this connects to the next thing I want to talk about, our sort of main event for tonight. If you look at where the Pleiades are, this is the Hertzsprung-Russell diagram, right? This is kind of the Rosetta Stone for understanding stars, basically. And basically what it is, it's on this axis is star class and temperature, right? From cool stuff down here to super hot things up here. And on this axis right here is their luminosity, which is how bright they really are. Not the magnitude, right? That depends on distance as well. This is how bright they actually are. And they form a real kind of interesting pattern here called the main sequence. And if you look at where the Pleiades are in the main sequence, they mostly fall up here in the kind of hotter, brighter stars, right? Which makes sense because they're young and full of vigor. But it turns out that these have been useful in calibration in another way, for another application. And that kind of brings me to what I want to talk about. Okay, so before we go on, questions? Anybody? Additional comments? And by the way, if you got something you want to hear about, please tell me. I mean, I'm always looking for ideas. So these things.
There's an idea where it was thought that the Romans used to use the Pleiades as a sight test, and if you only could see 5 stars, you were a cook.
Yeah. I'd say I can only see 3. What does that make me?
Trash.
That probably makes you a target. Like you become like the guy on the football team that holds the tackling dummy for 3 minutes. But anyway, Anyway, I've heard that. I think I've heard that too. Now that you mention it, that and I know it's not the Pleiades, but the middle star, the Big Dipper handle, and what is that, Mizar?
Mizar.
Yeah.
Those have been used as sight. It's one of my markers of kind of deterioration that I can't separate them anymore. I used to be able to, but can't. So anyway, but yes, that's another thing. Okay, so what I wanted to spend the rest of the evening talking about is distance scales, and in fact, as we're going to kind of see, these two stories maybe mesh into one another just a little bit. And in particular, I want to talk about what's called the cosmic distance ladder. And again, I'm going to preface this by saying, we're going to talk about this for another half hour or so. And we're not going to get all the details out there because this involves more than a century of astronomy and some of the most eminent astronomers, and a few that are probably not as well known, but really deserve to be. So we kind of get into some of the science here, but there's also just a super amount of history involved. This is one of the reasons why I thought it would be kind of an interesting thing to talk about. So anyway, let's begin with finding D. So you see things like this all the time, right? Stars, and they're this many light years away, right? The closest star to Earth, 4.2. Brightest star, 8.6. Polaris and North Star, 431 light years. When you get further away, you start getting galaxies, you know, hundreds to millions of light years away. Further and further out there, we start getting to things that are billions of light years away. And it kind of raises a question of, like, how do we know that, right? It's pretty easy to figure out where something is in terms of position, right? But that, you know, the X and the Y, if you want to think about it that way, that's not too tough. But the Z, man, that's a different kind of thing, especially if you know, don't have a really long yardstick that you can hold out there or something like that. And so, as I said, establishing the scale for all this has been a major undertaking in astronomical science, probably for well over 100 years, and involves some pretty clever thinking, and that's what I wanted to kind of spend a little bit of time with. So hopefully by the end of this little spiel here, we'll at least have a little bit of a better idea about how we know this stuff. And this is typically referred to as the cosmic distance ladder, and the ladder is not a poorly chosen analogy here, because like a ladder, right, if you want to climb a ladder, you got to step on one step and the next step and the next step, and the steps depend on each other. In this case, it's even really more of a ladder because they're interlocking, right? In order to establish one rung on the ladder, you have to have a really good understanding of the previous rung. And so I suppose that how many rungs you choose depends a little bit on, I guess, what you consider a rung. But I thought this was a pretty good guideline here. I don't know who made this diagram, but I thought it was a pretty good one. So I'm just going to follow this. We're going to start down here with the closest things, which is actually a more recent rung, really. Probably the most, the first rung was probably this one right here, actually, the first astronomical rung. But I'm going to kind of take these in order, and we're going to look at what each one of these is and a little bit about how they work. And we'll start off with this, this rung right here, which is called radar ranging here. I actually think of it as more of, as a form of active remote sensing. But before we do that, it's kind of useful to think about what we mean by distance, because it's not as simple of an idea as it might be than if we wanted to measure, you know, the distance from across this table or something, because the universe is getting bigger as we measure it, all right? And so you kind of have to think about distance. So there's two ways that distance is, and mostly this matters when you start getting into cosmological stuff, right? Very large scale. There's two types of distances, what's called proper distance and then what's called co-moving distance. And so the difference between those is the co-moving distance kind of stays the same, right? Through and the proper distance depends on expansion. So what D means in most contexts is it's the proper distance, or it's the co-moving distance at the current time. And again, that seems kind of, you know, hand wavy, right? But you can sort of imagine if you had two fixed objects, and again, nothing in space is really fixed, right? But if you imagine you have these two fixed objects some distance apart, in an expanding universe, they're going to get further apart, but that's not because of proper motion. It's not because that they're physically moving away from each other. It's just the whole thing is moving. So typically when they talk about distances, that's what they mean. So we're thinking about it as co-moving distance at the current time. So that's what the distances I'm going to refer to mean. Okay, so with that said, let's look at some of the distance ladder. And like I said, in some ways it might make more sense to start here if you're looking at this historically. But I'm going to start with this, with these shorter distances here. So if you look at the scale, they're talking about 10 to the minus fourth light years. That's like what, 0.0001 light years, which is, you know, somewhere in the light hour range, I guess. So we're talking about relatively short distances here, relatively, right? And it's identified on this as radar ranging, but I kind of tend to think of it as active remote sensing because of my particular background. And really the idea here is that you measure the distance by sending a beam of energy out there and reflecting it off of something and timing how long it takes to come back. And you know that that beam is going to travel at a particular speed. And if you can precisely make these measurements, you can get pretty good estimates of how far these things are. I think this is how, when they estimate the distances to a lot of like asteroids and stuff, this is how they're doing it. They're hitting it with a radar beam. You can do a similar sort of trick with light. That's called LiDAR. And the deal there is you send a laser. Now, of course, the problem with a laser is that in order to work effectively, it has to bounce off of something. So back in the 60s, astronauts left reflectors on the moon, and if you have a powerful enough laser, you can go out and bounce your own light off of it and measure the amount of time it takes to get back and know the distance very accurately. These are very accurate measurements, provided you understand, the way beams of electromagnetic radiation behave. All right. This is, for instance, how we know that the moon is getting further and further away, but not by very much. So this only works on the short thing. It takes a lot of energy to do this. It takes a tremendous amounts of energy to shoot a beam of radar out into space, and even more energy to shoot a laser. So this is not something that's practical for very long distances. One of the major places where they did a lot of this was the Arecibo antenna in Puerto Rico, which collapsed not that long ago, and is now just a big hole in the ground. That was one of the major things they did there. I remember visiting there and seeing the thing they used to shoot the radar beam and thinking, man, that's monstrous. It's a huge antenna, basically. Anyway, so that's the shortest. That's kind of rung number one in a way, and it really is only effective for things that are fairly close to us. That second rung is where the game really starts in terms of what I would think of as more astronomy and not so much just shooting beams of stuff. And so rung number two is what's called parallax. It makes use of what's called parallax, which is a use for trigonometry. So if you ever took trigonometry and wondered, why am I learning this stuff? Well, one of the reasons that you might learn it is if you want to figure out how far away something in space is, all right? Here's a little trigonometry joke right there. Everybody get it? Anyway, parallax. So basically what parallax is it's a change in position of something depending on a change in the observation. And one of the best ways to demonstrate parallax is kind of what this picture shows right here. So if you take your finger and hold it out and look at it with the one eye and then look at it with the other eye and look at it with this eye and look at it with that eye, it looks like it jumps back and forth, right? And if you then bring it closer to your face, it looks like it moves even further relative to what's behind it, right? And if you get even closer, it looks even further. And if you had super long arms, eventually you'd reach a point where it doesn't really look like it moves very much. And that becomes the limiting factor for your ability to detect parallax with your eyes. And so the idea behind parallax measurements is really just follows from that. So here's how trigonometric parallax works. So the Earth is orbiting the sun, right? We know with a fair degree of precision how far it is to the sun, which means that we know with a pretty fair degree of accuracy this distance right here. So the deal with parallax is you photograph some object against its background, right? Which we're making an assumption here that the background stuff's not moving, which it probably is, but probably not fast enough to really matter. And then 6 months later, you do the same, you repeat the process. So in December, you're looking at it from that angle. This is obviously a very exaggerated diagram. And so this foreground object's going to look like, over here somewhere against the background, and then here in June, 6 months later, it's going to look like it's over here somewhere. And if you know this angle right here, which you can figure out because you kind of know that one, right? Remember all that geometry stuff about similar triangles and all that kind of stuff. Then you know that angle right there. And if you know that distance right there, which you kind of do because you know how far it is to the sun, basically, then it just follows, right? All that SOHCAHTOA stuff comes into play, and you can figure out that line right there. Of course, the limitation on all this is you have to be able to accurately measure that angle right there, which means you have to make very, very accurate astrometric positional measurements of these stars. And it depends, of course, on the distance. Close stars have big parallaxes. Further away stuff has smaller parallaxes, and eventually you reach a point where the angle becomes unmeasurable. And it turns out that happens at a limit of about 100 light years. So what that means is you can measure stuff that's within about 100 light years pretty accurately using this method. And there are actually telescopes that are dedicated to doing this kind of thing. If you ever get a chance to visit the U.S. Naval Observatory in Flagstaff, Arizona, they have a very large telescope that's basically optimized to measure for astrometry, to measure positions of things. And one of the things, of course, the Navy is into astronomy because they want to navigate, right? They want to accurately know where things are. And that's why they built that pretty big telescope, was to measure this kind of stuff. So that doesn't get you out very far, but it does a pretty good job of making those measurements. So its advantages are you can get much, much further out than those remote sensing things are, right? If you send a laser, provided you could send a laser beam 100 light years, it would take 100 years to get there and 100 years to get back. So you got to write a note to somebody and say, in 200 years, will you please receive my, not very practical. So it's capable of much greater distances. Oddly enough, it's not that good for things that are too close, but that's just a quirk of Earth motion more than anything else. It's more, I guess it's a direct measure, right, of distance. You're not estimating it in terms of something else. You're actually estimating it in terms. And I mean, surveyors on Earth use this kind of stuff all the time, right? So this is not, this is not rocket science. And it's conceptually pretty simple. All you need is trigonometry and good position measurements. Of course, the drawbacks, relative to limited range, you have to have extremely accurate astrometric measurements, and not all, as I said, not all telescopes are really capable of doing that because of the way the optics are designed and that sort of thing. And finally, it gets less precise with distance because that angle gets harder and harder to measure. So the error bars around the distances get get bigger as you get further and further away. Nevertheless, this is a method that's been in use for quite a long period of time, and we know a lot of stuff, the distance to about 50,000 objects because of parallax. There's a satellite called Hipparcos now, which is a parallax measuring satellite, and it's kind of revolutionized a lot of this distance stuff. And that actually brings up another thing that's kind of important to remember about the distance scale, which is each rung depends on the previous rung. So in research, we refer to that as error propagation, right? Errors become bigger errors, become bigger errors. And so there's constant effort to try to control error at all levels of these things in order to kind of make those measurements just as accurate as possible. Anyway, so that's parallax. That's that kind of the first astronomy rung in a way. So what do you do if you are further away than that? And this is where it gets a little bit more into, not so much into the kind of traditional astronomy of measuring things, and more into the physics of astronomy, of understanding the physical nature of the things that you're actually looking at. And so the next rung, if you will, brings us back to the Hertzsprung-Russell diagram, which we just saw a few minutes ago in a somewhat different guise. So again, just to kind of remind ourselves here, we're looking at what's called the color index here, which tells us something about the color or the temperature of a star, right? The color's closely related. And the absolute magnitude or the luminosity, right? How bright they really are. And so most stars follow along this thing called the main sequence right here. And so if we measure the Hertzsprung-Russell diagram for a cluster of stars, you see where this is going? If you measure the Hertzsprung-Russell diagram for stars in a cluster, you can say something about their intrinsic brightness, right? So if you can meet these assumptions that all the stars in the cluster form from the same matter cloud, again, can you kind of see where we're going with this? And that the stars are in the cluster are bound together by gravity, right? So they are truly a cluster. And that they are all found generally in the same location on the Hertzsprung-Russell diagram as stars in general. In other words, if you plotted these cluster stars on the Hertzsprung-Russell diagram, they're going to show up somewhere in this main sequence, right? And then this is kind of the key point. I hope you can see this. You have to have relatively nearby stars that you can measure using the previous rung, that you can measure using parallax, so that you have another way of establishing that distance. Then you can use kind of a clever trick of what's called cluster fitting, which means that you basically use some sort of reference cluster, one that you know the distance to. You take your new cluster that you're trying to figure out the distance to, and you assume that they are physically similar to one another, right? And so the distance between them, the difference in brightness between them, is called the distance modulus. And it is indicative, it's a relative measure of how much further away that cluster is than the one you can accurately measure the distance to. Does that make sense? So, good example of that is our old friends, the Pleiades and the Hyades, right? The Pleiades are close enough to be measured astrometrically. The Hyades are not, but they are composed of very similar types of stars. So here's the main sequence for the Pleiades, right? Again, these are very hot stars, right? Most of the Pleiades are way up here on the temperature scale. Sun would be like down here somewhere. Here's the Hyades, very similar. The distance modulus is 7.5, which means that by comparing the brightness of stars in the Pleiades to the brightness of similar stars in the Hyades, the ones in the Hyades are enough dimmer, apparently, that it suggests that they are 7.5 times further away from the Earth than the Pleiades are. So if you know how far the Pleiades are, you multiply that by 7.5, you get the distance to the Hyades. And by doing this, you can kind of measure the distance to clusters of stars. And then if you figure out, well, this thing is pretty close to this cluster, this star is pretty close to that cluster, you get a measure of how far away things are that are farther away than what can be done astrometrically, but you're using the kind of physical nature of the star. So this is called cluster fitting. It's effective to about 10,000 light years. So astrometry got us to about 100 light years. This is getting us, 100 times further than that. Advantages here, bigger distances, obviously, major advantage. This takes us a pretty long way out into the Milky Way, right? We can't get out to other galaxies yet, but it takes us a pretty far out into the Milky Way. Makes use of a very well understood physical model of stars. The Hertzsprung-Russell diagram is a kind of, like I said, it's like the Rosetta Stone for understanding stars. It tells us tremendous amounts about their physical properties, and it makes use of that. And it's also kind of standard observational astrophysics, I guess you could say. The astrometry method was standard astrometry, right? Star measurement. This is kind of measurement of physical properties, like how bright they are and what their spectral response is. But again, this is stuff that is very well refined, right? This doesn't involve much in the way of cutting edge observation. So those are the good stuff about cluster fitting. Bad stuff, you got to have parallax measurements to suitable calibration clusters, right? Pleiades, Hyades, for example. Stars that have evolved off the main sequence can really mess this up, right? The main sequence, again, is this part of the Hertzsprung-Russell right area, and as stars age, they kind of move off of it. They move through this thing called the instability strip, where they become variable stars, and they become giant stars. There's Betelgeuse right there, huge, red, relatively cool star. So if you've got stars in your cluster that are off the main sequence, they can really mess this up. It must be main sequence stars in order to work. You get these things called blue stragglers, which are not, they're stars that should be in the main sequence, but are not for reasons that we won't go into, but they can kind of screw you up here a little bit too. And then stars sometimes appear to be in a cluster and aren't, right? Just because of line of sight, right? So that's another potential problem with this. But if you can, meet all these requirements, you end up with a distance metric that's, pretty effective out to a reasonably long way. Okay, so that's rung number 3, I guess, so far. And it's like astronomy rung number 2 or astrophysics rung number 1, if you want to think about it that way. Okay, so let's take a little break and think about something else here for a second. The relationship between distance and brightness of things starts to come into play when we start looking at these physical properties. And we know, you know intuitively that as you get further and further away from a light source, the light source starts looking dimmer and dimmer, right? Turns out that there's a very well understood physical relationship there. It's called the inverse square law, which says that if you double the distance between something, it becomes 1/4 as bright, right? It dims as a square of the distance. And so if you knew how far away something was, or if you knew how bright something was intrinsically, and you measured its brightness, you could kind of get an idea of the distance, right? So if, for example, if you took this light bulb and you knew it was, 40 watts, whatever that would translate to into lumens, which would be an actual measure of brightness. If you knew that, and then you started measuring its brightness at various distances, you could, or you measured it at unknown distances, you could tell what that distance was just by comparing how much you measured to what the intrinsic brightness was. So that would be a great way of finding distances to things, except you have to know how bright they are. And that's the problem, because all 40-watt light bulbs have the same lumens. It's on the box when you buy it. Stars and objects in the cosmos come in lots of different brightnesses for lots of different reasons. And that's part of the problem. So in order to kind of calibrate a distance scale, you have to have what's called a standard candle. And a standard candle is just something that you know how bright it is. So in order to get further into the distance scale, it became necessary to start finding standard candles. And the discovery of standard candles was actually one of the seminal events in the history of observational astronomy. So it turns out there are some things that work pretty well as standard candles, and one of them is what's called a Cepheid variable. So a Cepheid variable is a type of variable star. A variable star is a star that gets dimmer and brighter for a variety of reasons, but a Cepheid variable gets dimmer and brighter because it's physically getting bigger and smaller and bigger and smaller. The reason, again, why that happens, we don't necessarily need to go into. But what characterizes a Cepheid variable is that it has a very fixed and predictable pattern for dimming and brightening. So Cepheid variables, probably the most famous or well-known example is the Polaris. The North Star is a Cepheid variable, right? So if you watch the North Star for a long enough period of time, it will become visibly dimmer and brighter. You can tell by looking at it. And so there's Polaris A, it's a Cepheid variable. So here's the deal with Cepheid variables, though. There is a very well-established relationship between the period at which they dim and brighten and their intrinsic luminosity. And the person that discovered this was this woman, Henrietta Leavitt. So Henrietta Leavitt was what was called a computer for the Harvard College Astronomy back around the turn of the last century. And she was given the computer's task, which, in those days computers were not machines, they were people. And basically what they did was, arithmetic all day. And she was given the task of studying this class of variable star, or collecting data. And one of the things she noticed, and she was probably just an incredibly gifted person, was that there was a very distinct relationship between the period and the brightness, right? The brighter the Cepheid, the longer the period, and vice versa. And the relationship between those was very linear. This is actually some of her original data from the Magellanic Clouds. This actually came along a little bit later from the population of stars that she was actually studying. But what she found was that there was this relationship between those things. And this was an amazing discovery, right? This opened the door to a lot of understanding about how stars work. But it also opened the door to the next rung in the distance scale. So this guy, Harlow Shapley, who was also at Harvard College Observatory later, I think, than Henrietta. Henrietta died relatively young. She had kind of a tragic life in a lot of ways. But he realized that if you could sort of calibrate this scale, you could use this linear relationship to standardize the candle. You could say with accuracy what the intrinsic brightness of a Cepheid variable was. If you knew its period, you knew how on the scale at which it lightened and darkened, right? And so what he did was he calibrated them against a type of star called an R. Lyrae star, which is a very, very stable star. They don't vary in brightness very much. A lot of R. Lyrae stars were understood, and their distance was known. So Shapley used R. Lyrae stars to kind of establish the scale, and then he used this linear relationship between Cepheids and luminosity. That's intrinsically how bright they are. This is, by the way, is luminosity scaled to the sun, right? So one would be as bright as the sun, and this would be 100 times brighter than the sun, and so on. And the period at which they fluctuated. So what Shapley was interested in was finding the distance to globular clusters. And so he was measuring Cepheids in globular clusters, and what he got out of all this was essentially what the shape of the Milky Way is and how big it is, because globular clusters kind of form a halo around the Milky Way galaxy. They kind of knew that back then. So he used it basically to establish that the Milky Way galaxy was a big flat thing, and about what the size was. Where the story kind of enters into the cosmic distance scale was a little bit later than that, and the lead on this was this guy's Walter Body. Walter was a German astronomer who worked at the Mount Wilson Observatory in the 30s and 40s. And at that time, Mount Wilson was the kind of the leading center for astronomical study. This was the 100-inch telescope there, which at that time was the biggest in the world. And one of the things he was interested in was seeing if you could use this relationship to find the distance to the nearest galaxies. Problem was that this was right at the right near the limit of resolution for this telescope. Plus, even then, this was back in the 30s, early 40s, even then, Los Angeles was starting to get big enough that its light was beginning to interfere. So they couldn't quite do it. And they were also limited by the abilities of photographic film, because they were doing all this by photography. Electronic sensors didn't exist yet. But something came along in the 1940s that changed all that. What do you think it was?
Radar.
No, not necessarily. What big thing happened in the 1940s? World War II. And it turns out that what happened here was two things that really worked in Walter Body's favor. First of all, he was German. He was a German citizen, so he was considered an enemy alien, although he was probably about the opposite of a Nazi, right? But he was considered an enemy alien, so a lot of the astronomers and scientists and people who worked at Mount Wilson got drafted, essentially coerced into serving in the military in some research capacity. Walter was exempt from that because he was considered an enemy alien. He was, however, allowed to keep working at Mount Wilson. He was assigned an MP who would take him up to the mountain every clear night and probably snooze while Walter did his thing. And that guy was probably the luckiest person in the U.S. military during World War II, because all he had to do all day was drive Walter Body to the top of the mountain. The other great thing that happened was that there was blackouts, right? So Los Angeles even then was a major center for like the aircraft industry, so people were assuming it was going to get bombed at some point, so they blacked everything out, blocked all that light. So now you had this really clear dark sky, you had this state-of-the-art telescope, and you had all the time in the world to use it. And so what Walter started to do was look for Cepheids in other galaxies, particularly in Andromeda. And he found them. But the problem was that he was getting distances that could not possibly be right. They basically would indicate that it was further away than the edge of edge of reality. And it turned out that the problem with that was that there were these two populations of Cepheids, and nobody quite knew that then. This is how that got figured out. So they went back, recalibrated the distance scale, and started to get pretty good distances to pretty accurate distances. And that information then got used by Hubble. First name was Edwin, maybe? And of course, what he did was use those distances to calibrate this scale that related the speed at which the universe is expanding to distances related by this thing called the Hubble constant. And debate about the Hubble constant has been going on ever since, but the distance scale that got established for making these kinds of things was largely based on Cepheid variables and relatively nearby galaxies. So this is kind of pointing to where what the purpose of all this stuff is. I mean, it's nice to know how far away things are, but it's crucially important for a lot of astronomical science as well. Okay, so here we are. We have gone through parallax. And that gets us out to hundreds of light years. We've gone out to main sequence fitting, and that gets us out to tens of thousands of light years. And we've gone to Cepheid variables. That gets us about 10 million light years away. That's a long way, but it's not really to the edge of the universe by any means. So how do you get even further than that? And that's when we get out to these methods that, Cepheid variables, you're looking for Cepheids in other galaxies, and there's still really active research done in this kinds of work. If you want to get any further than that, now you're starting to measure distances to galaxy clusters. So if you're kind of figuring out what a Cepheid variable is in a nearby galaxy, you say, okay, the distance to that Cepheid is something, and it's in that galaxy, therefore that galaxy is about that far away, right? Now we're starting to look at the largest structures there are, these clusters, massive clusters of galaxies. And the relationship here actually turns out to also be kind of a physics thing, but instead of dealing with the brightness and dimness or the dynamics of individual stars, now we're looking at the dynamics of whole galaxies, and particularly how fast they rotate and how big they are. And the kind of key to this was work that was done, I believe, in the late 60s and early 70s by Brent Tully and a guy named Fisher, whose first name I don't know. They came up with this thing called the Tully-Fisher. This was brand new when I was in college. This was stuff that was still state-of-the-art then, so I kind of remember it from there. But this is how this works. By the way, this is kind of the advantages of Cepheids. I guess this slide should have been before this one. But Cepheids are bright and easy to find. On the other hand, they're rare and they don't live very long because they're big, bright stars, which, big, bright stars have shorter lives. That period luminosity relationship is very well understood. It's gotten extremely well calibrated. Problem is there's two types of Cepheids, and their calibration is different. So there's two different populations, and you have to make sure you know which type you're looking at. Makes use of those standard techniques, right? But it doesn't work if the galaxy is so far away you can't make out Cepheids. That was one of the really kind of things that the Hubble Space Telescope sort of supercharged a little bit. It made it possible to see Cepheids further away than ground-based telescopes could. So it's effective to about 10 million light years, which is a long way, but it's not that far. Okay, so the next rung, which I called rung 5A because I think of the next two as sort of co-rungs, they work at about the same distance, is this relationship between galaxy rotation. So what Tully and Fisher found, and then later there was work by Faber and Jackson that kind of works with a different kind of galaxy, was that there's a relationship between the measurement of galactic rotation and the absolute magnitude of the galaxy. And again, it's a pretty tight linear relationship. Scientists love lines, right? Love linear relationships because they are easy, right? Fitting a line is a super easy thing to do. So what Tully and Fisher did was relate actually the log of the rotation velocity to the absolute magnitude of the galaxy. And then if you know the magnitude of the galaxy, then you can use that inverse square relationship and you get to it that way, right? So the trick of this then is you've got to be able to measure the galaxy's rotation. And that turns out to be kind of a tricky thing to do, because if you look at galaxies far enough away, the early studies of galactic rotation and things like the Andromeda Galaxy, you could actually measure the redshift of stars on one side and the blue shift of stars on the other, compare them to each other. When you start getting the galaxies that are in clusters, that are far enough away to be in clusters, it's hard to separate all that stuff out. You don't get that kind of detail. But it turns out that if you look at if you observe the light coming from one of these, it's an amalgamation of blue and redshifted and unshifted light. So the blue shift would be coming from the parts of the galaxies that are approaching, right? And the red would be the part that's further away. It's all kind of mixed together. So what Tully and Fisher figured out a way to do is unmix those things, basically to use the spectral properties of the galaxy, the spectrum of the galaxy, to kind of unmix those things. So they came up with a pretty clever way to measure galactic rotations without actually having to see the interior of the galaxy. And so what they began to use that understanding to measure the distance to clusters, things that are huge distances away. And they found, in some cases, clusters that are just monstrously huge, and distances to those. So, advantages here: you can use it to estimate very distant galaxies, galaxy clusters, stuff that is super, super long distances away, because that spectral unmixing technique, all you got to have is the light. You really don't have to be able to get the details of the interior details of the galaxy. All you need is the light coming from it. It's based on a physical relationship, right? That Tully-Fisher and the Faber-Jackson relationships between rotation and velocity. And so you can, again, use standard observational methods. You're collecting data using, you have to big telescopes to do this, and really good spectrometers, but fundamentally they're the same tools, right? The drawbacks of this is that whole idea of the relationship between rotation and size applies in general, but as ever, the devils are in the details, right? And there are situations where it doesn't apply. The other thing that turns out to be a little bit of a problem is that galaxies are made out of a lot of mass that's not luminous. It's not glowing, right? It's not baryonic matter, it's dark matter. And that affects the mass of the galaxy, while not necessarily affecting and therefore the rotational velocity, without necessarily affecting the luminosity, how bright it actually is. So all this has made the measurement of these a difficult one to do. Kind of got a lot of pushback very early in its relationship. One of the most famous observational astronomers of the 50s and 60s was Alan Sandage, who was one of the real stars of the Palomar Observatory. He hated this. He referred to it as the Fishy-Toller relationship. And I think Tully and Fisher essentially won that argument, but it took a while for the kind of old dudes to, accept the fact that this thing actually. Yeah. So that's galactic rotation methods. That's a rung that works very, very, very far away. Another rung that turns out works very, very, very far away are Type 1a supernovas. If you can see a Type 1a supernova in a galaxy, then you can use its brightness curve to tell you what its actual brightness is. This is a pretty well understood relationship as well. And it turns out that Type 1a supernovas are super bright, right? They make a lot of light to the point where you can see them in very distant galaxies. The problem here is that you have to catch it somewhere right near the peak of its brightness in order for this to actually work. So supernova methods also work to a very long distance. They are based on a physical relationship. They are standard observations. They're effective at galactic cluster scale, so 10, whatever that is, 10 to the somethingth, 10 to the billion, 10 billion light years, lots and lots of light years. Drawbacks: we don't completely understand the physics of Type 1 super, and by we I mean people that know this stuff, not me, don't really understand this. So the calibration is still a little iffy. Supernovae are very rare. Don't see them very often. And it only works on the supernovas at maximum brightness. So you got to catch a supernova, which is a rare thing at a rare moment in its development. But nevertheless, if you can make this measurement, if one can make this measurement, this works at about the same distances as do the galactic rotation stuff. Okay, so that's all the rungs. And that
Before
gets...
the surveys, the big surveys now, they're looking for supernova. Amateurs were the main ones to contribute because they had enough telescopes out looking at different galaxies that they could spot a new star pretty quickly.
Yeah, and that's actually one of the great things about amateur astronomy is amateurs have telescopes a go-go. There aren't that many professional astronomers. You know, there's like one telescope for every 300 of professional astronomers, and they spend a lot of their professional life fighting over who gets to use them.
Yeah.
It's not one of the more pleasant parts of the profession, to be honest with you. But anyway, it's so yeah, that's exactly right. And Supernova Patrol, which is just kind of looking for these things, is I think quite a few people involved in that, aren't they?
And they still are.
Yeah. So it's an area. It's one of many areas that amateurs make really significant contributions to. But as far as why we need to know all this stuff, well, if you want to know the size of something, you got to know how far away it is, right? Because you have to have a complete representation of its scale. If you want to know how bright it is, if you want to know what its mass is, if you want to know how it's moving, these are all things where the distance scale is absolutely necessary. So a lot of our fundamental understanding of things like dynamics, motion, expansion, all that stuff depends on the distance scale. And again, one of the things that really matters in all this is that one of the big unresolved issues in kind of understanding the universe as a whole is how fast it's expanding. Right? This thing called the Hubble constant. There's still a lot of disagreement on what the value of that actually is. The value that astronomers come up with by looking at stuff is very different than the value that they're coming up with by looking at things like the cosmic microwave background radiation, that kind of leftover noise from the Big Bang. So this is still a very active area of research. It's been going on for well over a century. It probably will continue to go on. One thing I will say though is, I just threw this in here. This is some astrometric parallax measurements using the Gaia satellite, which is a European space telescope. And these little arrow, I don't know if you can see them, these little arrow indicator, these error bars here. One of the things that some of this new technology is doing is it's making those error bars even smaller, right? So it's refining the ability to make these measurements. And so that's it.
Cool.
I keep thinking from a course I took at Washburn on relativity theory.
Uh-huh.
In Einstein's theory, there's something called a light cone, and there's a limit to where we can't get any information. So doesn't that limit how we can measure how big the universe itself is? Because information has to get to us.
Yeah.
And it's called the light cone. I remember taking the course at Washburn, and the diagrams of it showing information. There's a point where we'll never get any
There's
information.
no more. Yeah, you're past the.
So we'll never know
I don't know.
beyond a certain distance.
Yeah.
Because we're limited by the speed of light.
Yeah. I can see that. I'm not familiar with that.
I've seen the diagrams in the
Yeah.
books.
I have to take a look at that.
So,
But,
yeah, it's called, I think, a light cone.
Do you think as we, with things like Webb or these other missions that are pushing, how far we can see into the universe, because does that have the possibility of adding another rung onto?
I don't know. I mean, again, that's, unfortunately, this is not my thing,
Yeah.
so, all I know is what I read on the internet. But I would think so. I think, there's the thing about the Hubble, or I'm sorry, about the James Webb is that it's designed to look back to almost to the Big Bang, right? It's optimized to see longer wavelengths because it's looking for stuff that's deeply redshifted. And so I'm trying to think back to that diagram that I saw when the thing was first launched, where you know, how far the Hubble Space Telescope could look back time, and then how far the Webb could go. And it was back to, you know, like a few 100 million years after the, yeah, something like that. And I think when you get far enough back in time like that, you know, the notion of how far away things are becomes a little less clear to me, because you know, it's that trade-off of distance and time. But yeah, I know there's a millimeter wave telescope in South America that measures the background radiation, and they're looking for real fine fluctuations because they're trying to basically calibrate that Hubble flow. And then what they're seeing is not agree all that closely with what observation is seeing, and that's apparently, one of the articles refers to it as the crisis in cosmology. Maybe that's something Bharat could talk about.
Is that the Atacama Desert?
Yeah, that big,
Big, right?
yeah.
Bunch of them down there.
Yeah, it's in the Atacama because it's high and dry, and they're looking for microwaves, which, you know, the Earth generates a lot of microwaves, and it kind of depends on how wet and hot things are.
Their average humidity is like 4.
Yeah, it's never rained there in over 200 years, so it's about as dry as it gets. But they built this thing, it's more like a radio telescope than an optical one, but they built it with this sort of fence around it that blocks emissions from the ground, because that would just totally screw it up otherwise. So it's a pretty clever idea, actually. Anyway. All right, well, that's all I have
That's
to say.
cool. It's interesting.
Questions, comments? And again, as ever, if anybody wants to come and give a talk, I'm always willing to yield the floor. If you have a subject you would like to hear about, and
Yeah.
you give me enough time, I can see what I can do with it. But
I got a question.
mhm.
That, and I forgot it already because I'm damaged. The Tully, you know, that.
The Fisher Tully,
Yeah.
Tuller.
When was that established, or when did they release that?
I'm guessing it was sometime in the mid-'70s that they started, because it was a thing by the time I was in college. I mean, we learned about it. So
And they're
that would
still
be-
arguing about it, which should be about right.
I heard a podcast not too long ago that Brent Tully was the guest on. It was some astronomy podcast, and they were talking about they'd found this largest thing in the largest cluster of galaxies, and they gave it a name, and I can't think of what it's kind of an interesting name that they gave it, but he was talking about, you know, how they've used this method to kind of map the three-dimensional structure of this thing. I mean, it's fascinating stuff to me. It's all very hard for me to grasp, you know, because the distances and just the cleverness that went into figuring all this stuff out is just amazing to me. But anyway.
Cool.
Cool.
Okay, so again, next month, I will hope that we have